So this is the first seminar of the series of lectures named Kinematics of Spacetimes and Tidal Heating in the Presence of Torsion. So today I will talk about basic ingredients for congruence evolution. So this series of seminars will be divided mostly into two parts. So first is kinematic times, and here we will slowly learn how to derive the congruence evolution equations. So we will cover both time-like and null concepts. So what did I mean by congruence? By congruence, I mean the non-intersecting geodesics. Specifically, a bunch of non-intersecting geodesics. So I will first describe the definitions, notations, and also scope and motivation for this lecture. And slowly we will develop the machinery we need, mainly mathematical foundation, to calculate the congruence evolution. And also we will check if singularity avoidance is possible in a collapse. Yes, and in the section of this tidal heating, we will calculate the Hartley-Hawking tidal heating formula. So everything will be done in a setting that we have non-zero antisymmetric part of the connection. That means we have torsion. So this is the scopes of these seminars. So what is the motivation? So we know that a geodesic equation can serve us well to determine how a particle or light propagates in a space-time. But when we have a bunch of curves, a bunch of geodesic instead of a single geodesic, so how these curves propagate in a space-time, that can be determined by Raychaudhuri equation. So Raychaudhuri equations is basically the congruence evolution equation that we intend to derive here. And for this, we need some mathematical tools to establish first. So also, we know that the basic GR and how to extend the GR beyond Einstein equivalence principle. So to do this, we need to go beyond basically Lebesgue connection and find some generic connection. So first, let us define the covariant derivative of a vector. Yes, so here this C is a generic connection. Delta is the partial derivative, and x beta is some vector for vector, let's say. So we have here only one condition, that is zero non-metricity. That means that we have this condition where G is the metric. So we say that the metric is unchanged if we just take the covariant derivative. So we can assign local Minkowski spacetime to each point of the spacetime. So how this generic connection can be written? We can write a generic connection as where this gamma, capital gamma, gamma alpha beta is Lebesgue connection. And K alpha beta gamma is the contortion. So this is because this Lebesgue connection is purely symmetric one. So we have no constraint whether it has to be symmetric one. If we not in GR, then we can write that it can be written generically as Lebesgue part plus some contortion, which is antisymmetric part basically. So this contortion K alpha beta gamma can be written as the combination of torsion tensor where S is so S is basically antisymmetric part of the generic connection. So S is called torsion tensor, was first introduced by Eli Cartan. So we can say that a generic connection can be written as the combination of Lebesgue connection plus some contortion tensor. And this torsion tensor is basically antisymmetric in its first two indices. So we can write this. So now we have, let's say, two vectors. One is V and one is U. So let's check how we can define Lie derivative of a vector V along another vector U in a space-time where torsion is non-zero. So this is the definition of Lie derivative of V along a vector U. And if we use the definition of if we use the definition of covariant derivative, and if we substitute this this part basically del alpha U gamma and it should be V, del alpha V gamma and del alpha U gamma from this expression, then we will arrive. We have to do few steps, and then we can get there as u alpha del alpha v gamma Yes, so we see that this expression for Lie derivative of vector v along u can be written as this. And here we know that this S is a torsion tensor. So it is not the same if there is no torsion. And now we have to check, we have to define a few definitions of Riemann tensor, and also how we can define the covariant derivative for, commutator of covariant derivative. So if we also check for commutative of covariant derivative, let's say for a vector W gamma, then it can be written as alpha, beta, gamma, rho. Yes, so we know this relation very well, because we know that commutative of commutator of covariant derivative is just this if we are in GR and we have some extra term due to presence of torsion. So this is the modification due to the presence of torsion. Now we will go to the section, let's say evolution of separation vector. So let's say we have a bunch of curves. And that curve can be named as gamma S lambda, where S is changing with each curves, and gamma lambda is basically parameterizing each curve. So what I meant that we can define a tangent vector to the direction of flow u alpha, and a separation vector can be defined as epsilon alpha. So u alpha can be defined as del x alpha lambda, and separation vector can be defined as. So basically in this direction, S is changing. That means we are basically going from one geodesic or one curve to another curve. And each curve is parameterized by lambda. And if it is a geodesic and it is affinely parameterized, then we can say that lambda is a affine parameter. So for geodesic, we know that the acceleration, let's say alpha, yes, it should be proportional to u beta. And if it is, this is for geodesic, and if it is affinely parameterized, then we have to put another condition that it should be equal to 0. So acceleration is 0. So when we derive this convolution evolution equation, then basically we first calculate for a general set of geodesics, not putting acceleration to be 0 exactly, from the beginning. So we consider, and then we can put the acceleration to be 0 to have more specific equation for the evolution of congruence. So here now we calculate a few other things. So basically we can see that this separation vector, this xi alpha is basically telling us how the distance between two adjacent curves is changing as we propagate through the curves. So how we define this in a setting with torsion. So we first calculate this Lie derivative of this separation vector along the tangent vector. And here we can, define that, we already have defined that this u is the tangent vector and xi is the separation vector. And we can prove that this is 0. So let us try to prove this. So this is basically L psi u will be u alpha del alpha xi alpha del alpha u alpha minus u alpha del alpha xi, sorry, it should be beta, it should be beta. So if we sub the expression for u and xi here, then we can clearly see that this will be 0. So as we already have derived the equation for a vector v along, Lie derivative of a vector v along u, so we can just take the definitions, our earlier, and if we just use this, we v instead of u because it's our choice, and this xi instead of u, then we can just write the expression. Okay, so we have here this is equal to 0 basically. So if we just change our this is basically LUV. So here, let's say V we substitute with U and U with psi, then we get, and then we calculate, then we just say that this is 0, this is 0, then we get that U beta nabla beta alpha to B beta alpha psi beta. So we see that how separation vector propagates through the space-time can be determined solely by the property of this B tensor, which is a rank 2 tensor. So the expression of B is nabla alpha U beta plus 2s gamma alpha beta U gamma. So we see that the expression for beta alpha beta, there is torsion tensor. So definitely it is not the same if there is no torsion. And this B it can be determined by calculating the covariant derivative of the tangent vector, and also there is a contraction of torsion tensor with there is a contraction of torsion tensor with the tangent vector. So now we will see in a Newtonian analogy how this B can be written. So if congruence is propagating through the space-time, what could be the effects there? So it can expand. So let's say we have a circle here, and it can get bigger as it propagates through the space-time. So this is basically expansion. So also there can be shear. So let's say we have some circle here, and it can be there can be shear, so it gets shrinked. Or there can be a rotation. You can say as twist. So now we will go to purely Newtonian context in a two-dimensional deformable medium, and we see how this B can be written as the collection of these three phenomena, as we just described here: expansion, shear, and twist. So in a pure Newtonian framework, if we just say that we can always write for a sufficiently small displacement, let's say xi a, so we can write d xi alpha dt is proportional to b a b t, right, b plus some higher order. So we will neglect this higher order contribution here. We will only stick to the first order. So if we just write the above equation in a difference equation, or let's say, then we can write we can write as the change in xi, as delta xi alpha at t0. So the time is basically changing from t0 to t1. So here delta t is basically T1 minus T0. So let's say we have a simple figure. Let's say we have a circle of radius R0. And this, if we write the circle of this a circle of radius R0 in component form, then it can be written as psi, let's say alpha T0 as R0 cosine phi sine phi. So let's say our system propagates through a deformable medium where time changes from T0 to T1. Then what could be the properties of B alpha B A B here? Let's say B is an identity matrix. So BA can be written as with some constant multiplied. We can here say that this trace of B alpha B, that is basically BAA, is theta. And if we have B in this nature, then basically we see we have here delta epsilon alpha is basically B let's say it's A. So, or maybe we can write in the other way. So alpha B alpha, let's say beta T0 epsilon beta T0 delta T. So if we have B like this, then we can calculate delta epsilon alpha, and this delta epsilon alpha for this case will be half theta R0 delta T cosine phi sine phi. So this basically tells us that we'll have a new circle with radius R1 equal to R0 plus half theta R0 delta T. Yes, so we can, this is the change in radius, and we already have here this, the previous, so the radius of initial radius. So if we just calculate this epsilon alpha plus delta epsilon alpha, then we will basically have what we will have 1 plus or R0 plus half theta R0 delta T cosine phi sine phi. So this tells us that we have a new radius R1, which can be written as this. And if we now check the change in area as the radius is changing, so definitely we'll have a change in area. So if we calculate the change in area, then let's say A1 is the new area and A0 is the old area, then we can calculate this will be pi R0 square theta delta T. Or in other way, it will be, so this is basically A0. because earlier radius was r0, so it's pi r square. It's the earlier radius. So you can say that theta is basically del 1 over a naught del a del t. So this theta is the expansion parameter. And it can be written as the change in area per unit time, or in a more concrete way, we can say that fractional change in area per unit time. Now let's say we have B something like purely symmetric and trace-free. So we can see that if we sum up the diagonal elements, then it is 0. So there is it is trace-free, and it is also symmetric. So basically, if we calculate the transpose of this metric, then we'll get the same metric again. And considering this B, we will basically have change in our separation vector. It will be R0 delta T and if we calculate the change in xi, so basically it will be xi 0 plus delta. Then we will have then we will have the xi, and if we just take if we just calculate the new radius, then the new radius will be R1 phi . Okay, and this is the parametric equation for ellipse. It is representing an ellipse. So we had a circle, now we have an ellipse. So definitely there is here which made some distortion, and due to the distortion, our circle become ellipse. So now let us check how the orientation will be depending on these CR parameters, sigma plus and sigma cross. So sigma plus, let's say, what will be the case when we have sigma cross equal to 0? So sigma cross equal to 0, then this term goes away, and we will have 1 plus sigma plus del t cos 2 pi. So if we want to calculate the length of semi-major axis, then this should be maximum, basically this term. And in order to be maximize this, we have to get the maximum contribution from cos 2 phi. So let's say cos 2 phi is 1. So that means basically phi equal to 0. So in this case, let's say it was our circle, and it has become an ellipse. So this it is oriented, I mean, the major axis is oriented along phi equal to 0. So you see that it is on the axis and completely aligned. And if we have, let's say, sigma plus equal to 0, then we have to maximize sine 2 phi, and sine 2 phi is 1. So that means 2 phi is pi by 2. So phi is pi by 4. And in this case, we will have something like this. So we see that here this angle is pi by 4. So this sigma plus and sigma cross, they are shear parameters. They describe how shear can influence the propagation of a bunch of curves in a space-time. And now if we just describe the rotation, yeah. Finally, we can propose that, okay, so our B metric can be a purely antisymmetric one. In this case, we have this. So you see that this is an antisymmetric metric. And if we use this B metric, then basically we will have the change in psi as R0 omega delta t sine phi minus cos phi. And if we calculate the new the changed psi vector, then basically we will have R0 cosine alpha prime sine alpha, yes, sine phi prime, sorry, sine phi prime, where this phi prime is phi minus omega delta t. So where delta t is the duration time changes from t0 to t1, and omega is the twist parameter. And this phi was the initial angle of the radius vector. So we can clearly see that there is a rotation. So this metric, matrix B can represent the twist in the congruence. So the most general form of B alpha beta in 2 cos 2 form, or in 2 dimension, we can write B alpha beta equal to so because of expansion plus shear plus twist. So we can write as a linear combination of twist, shear, and rotation. So it will be B alpha beta half theta beta sigma alpha beta plus omega alpha beta, where this theta is just the trace of B, and this sigma alpha beta is basically the traced out symmetric part. and omega alpha beta is completely antisymmetric part representing the twist. So this is expansion again, and this is the shear tensor, and this is twist tensor, or even sometimes called vorticity. Expansion, of course, it's a scalar. So we can write in this way, and in a 3D settings, only the change will be that it will be 3x3 matrix instead of 2x2. And here we will have this P alpha beta equal to 1/3 delta beta sigma alpha beta plus omega alpha beta. And in this 3x3 settings, or in 3 dimension, we can define this, not define, but it is kind of definition that this expansion parameter can be written as the change in volume, or in fractional change of volume per unit time. So this is the machinery. Basically, B, we needed to define B and also other definitions and notations in order to derive the evolution equation. So for expansion parameter. So basically, our goal is to calculate the evolution equation for theta, for sigma, and for omega in both time-like and null cases. So basically, we'll have kind of these, and in next lecture we'll derive this time-like case for both for all these parameters, like expansion scalar and also shear tensor and for a twist. In order to do that, we need to define a projection operator that projects this B alpha beta on the hypersurface orthogonal to the direction of flow. So that we will discuss in the next seminar. Thank you. So please go ahead if you have any questions.
Okay, thank you very much, Sudipta, for your